Welcome to my show called Space, Stars, and You. And in this show, there'll be no commercial interruptions, no product placements of any kind, or no egregious placements of any kind whatsoever. That's because I just have too much integrity and absolutely refuse to sell out. Well, so much for my integrity. Today we'll be discussing our cosmic address, that is where you live in the universe, how light travels, that is the speed of light, and how far things are away from us, and star cycles, which means how stars evolve. We reside in the solar system of the sun. Besides the sun, there are 4 inner rocky planets: Mercury, Venus, Earth, and Mars, followed by an asteroid belt, followed by 2 gas giants, Jupiter and Saturn, followed by 2 ice giants, Uranus and Neptune. This is followed by the Kuiper belt, where Pluto originates from, as well as short period comets come from, like Halley's Comet. This is followed by the Oort cloud, where longer period comets come from that are over 200 years in orbit. Our solar system is located in the Milky Way galaxy, a collection of 100 billion stars, a collection of 300 billion stars. It rotates once every 250 million years, and our galaxy has a diameter of 100,000 light years. If we can turn off that microphone. Thank you.
I did turn off.
Thank you. Sorry. We okay? Our solar system is located, thank you, in the Milky Way galaxy, which, our solar system is located in the Orion arm of the Milky Way, which is a small spur or tributary between the Sagittarius arm and the Perseus arm. We are 26,000 light years from the center, and this is a diagram of Kepler searching for habitable planets in the Orion arm. Actually, Kepler has found at least 400 planets that are not too far from us so far. Our Milky Way galaxy is located in the local neighborhood. It spans 5 million light years and includes Andromeda galaxy, some small nebula, and the large and small Magellanic clouds. This spans 5 million light years. Our local neighborhood is located in the Virgo cluster of galaxies, a collection of 2,000 galaxies. 90% of them are dwarf galaxies, and this spans 15 million light years. This Virgo cluster is located in the Virgo supergroup, a collection of 100,000 galaxies. It is called Laniakea for the Hawaiian term meaning unbounded heavens. This spans 550 million light years. And if you think by now our planet and our solar system is just a drop of water in an endless ocean, you are correct. The Virgo supergroup is one of countless millions of supergroups that constitute our universe. Our universe spans 92 billion light years. It contains over 2 trillion galaxies, and there is no "you are here" area, or up, down, or east or west. Everywhere you look and everywhere you are in the center. And our universe is thought to be in a multiverse. Think of soap bubbles in your sink. This is a controversial theory saying that there are other pocket universes that abound, and each have their own sets of laws of physics and their own dynamics. So this is your cosmic address: the solar system of the sun, the Orion arm of the Milky Way galaxy, the Milky Way, the local group of galaxies, the Virgo cluster of galaxies, the Virgo supergroup of galaxies, the known universe, and the multiverse. Now, I've thrown around some big ticket terms, and those really need to be explained to you, as well as we need to understand our cosmic address better. In order to do that, we need to examine the speed of light. The speed of light is 186,282 miles per second, which is the equivalent of traveling around the Earth's equator 7.5 times in 1 second. Light travels about 6 trillion miles in a year, and when it does that, it's called 1 light year. Now, whenever you see something, it's in the past, because light takes time to get to your eyes. When you look at your neighbor, it's 1/100th of a billion of a second in the past or from you. Now, the moon is 240,000 miles from us, and light travels at 186,000 miles per second. So the moon is 1.3 light seconds from us. Our sun is 9 light minutes from us. Mars is 12 light minutes from us, or between 40 and 60 million miles. Jupiter is 40 light minutes from us, or 500 million miles. Saturn is 72 light minutes from us, or 800 million miles. Neptune is 4 light hours from us, or 2.5 billion miles from us. And Pluto is 5.5 light hours from us. Now our nearest star is Alpha Proxima. It is 4.3 light years from us, or 4.3 times 6 trillion miles, which is about 25 trillion miles. Alpha Proxima is in the Alpha Centauri system. It is a red dwarf. It has a planet orbiting around it, and it has a companion star. Now there's a probe launched in the late 70s called Voyager. Voyager is not headed to Alpha Proxima, but in terms of distance and speed, the probe is going at 38,000 miles per hour, or 570 miles per minute, or 8 miles a second. And at that speed, it would take 10,000 years to get to Alpha Proxima. Now Lucy is here to tell us that we've been broadcasting radio waves for the last 100 years. Those waves have escaped into outer space, they've traveled at the speed of light, and now radio programs are 100 light years from us. TV signals have been broadcast for 75 years. They too have escaped into space, traveled at the same speed, and now the I Love Lucy show will be able to be seen in the Orion constellation in the Big Dipper in a few years from now. That's because the stars in the Big Dipper that make the belt of Orion, as well as the Orion constellation itself, are stars that are between 70 and a couple hundred light years from us. Some stars are 1,500 light years from us, and some are red giants that we'll be talking about later on. However, all the stars in the Orion constellation, plus other constellations like Leo and Gemini, Sagittarius, Virgo, those are all stars in the Orion arm of our Milky Way, all in general a couple hundred light years from us. Now, our nearest galaxy, or our sister galaxy, is Andromeda Galaxy. It is 2.3 million light years from us, or 2.3 million times 6 trillion miles. Andromeda is a much more robust galaxy than ours. It has a diameter of 250,000 light years, and it contains 1 trillion stars. And we're going to be talking about why the center of this galaxy, along with other galaxies, why they are so bright. That is why they are so luminous, later on in this presentation. Now, how just do scientists measure how far stars are away? Well, they use trigonometry. That is, they first measure the star, and then they wait exactly 6 months. They know how far, and they measure it again. They know how far the Earth has traveled in that arc. And then they compare the star to what the background stars are, and they use the two angles using trigonometry to find its distance. As for closer in galaxies, astronomers use Cepheid variables to measure their distance. These Cepheid variables are stars that dim and brighten over the course of a couple weeks or a couple months, and when they get a true brightness, they use them as light candles to determine how far away these closer galaxies are to us. As for further galaxies away, ones farther away, well, we use known luminous objects, and we use them as light yardsticks to determine their distance. Now, space is very much like a fabric. That is, when something cataclysmic happens in space, like two black holes collide, ripples are sent through the space-time continuum, much like ripples on a pond. These shock waves are called gravitational waves, and now can be detected by special instruments, even something that happened millions of years ago. And this month, the Nobel Prize in Physics was awarded to men who made a special device that was able to pick up these gravitational waves. And this year, they found gravitational waves that were detected by this machine. They came from two black holes that collided 1.8 billion years ago, which means the waves are still traveling through our universe, still reverberating through it, and this is very much in accordance with what Einstein had predicted in some of his theories of relativity and the general theory about 105 years ago. Also, that space If you put something very heavy in space, like our sun, it weights down space and becomes like a gravitational well. That's why planets to the inside of our sun orbit faster than planets to the outside. And lastly, that space is made up of atoms, and the distance between those atoms is increasing. That is slowly increasing. That is, space is slowly expanding. And we know this because we can infer it and measure it. But how we do this is that we think that there's an invisible force that's mysterious and invisible to us, and we don't know much about it. It's called dark energy, and dark energy comprises 70% of what our universe is made out of. And this dark energy, we believe, is responsible for the expansion of space. And we can infer that space is expanding, and we can measure that space is expanding also. Now, whenever astronomers look through telescopes, they see galaxies as slowly moving away from us, as in a very slow motion cosmic dance. If these dots on the balloon were galaxies, astronomers see something like this. That is, galaxies are receding from each other. And that the further a galaxy is away from us, the faster it's receding from us. And this is called Hubble's law, or Hubble's constant. And there's a direct mathematical proportion between distance and speed. This is how we know that galaxies are inferred, that galaxies are receding from us. And this kind of expansion in space is called cosmic inflation, or accelerated expansion of the universe, or simply inflation. Now, this is the Sombrero Galaxy, which is 29 million light years from us. And if we resided in this galaxy and we were astronomers here and we looked through our telescopes, we would see other galaxies like the Milky Way and Andromeda as slowly receding from us. And we would conclude or infer two things: that A, space is expanding, and B, that we must be in the center of the universe because everything is slowly drifting or ebbing away from us. Now, we can, besides inferring that the universe is expanding, we can also measure that the universe is inflating through dark energy with the Doppler effect. That is, when the spectral lights of the galaxies are examined through a spectrometer, those galaxies that are moving away from us have their wavelengths elongated or lengthened out toward the red end of the spectrum. That means that they are redshifted. When galaxies are coming toward us, their spectral lines are shortened or truncated toward the blue end of the spectrum, and we would call blue shifted. But all galaxies are redshifted. They are slowly ebbing away from us. And the Doppler effect is very much like a police siren. When the siren is coming toward us, the sound waves are shortened and it sounds very intense. However, when the police siren is going away from us, those sound waves are elongated and it sounds very faint. So all galaxies are receding from us and are redshifted except one, which is Andromeda, which will be coming toward us, is coming toward us at a speed of 75,000 miles per hour, and will eventually merge in with our galaxy in 3 billion years. But all galaxies are redshifted. Now, if this was all the light in the universe possible, we only see a couple inches of it, which is the visible spectrum or the rainbow. We need special instruments that are sophisticated and sensitive to be able to detect and measure rays like infrared rays and ultraviolet rays, as well as gamma rays and X-rays. Now, besides dark energy, there's another invisible force in the universe that manifests itself in galaxies, and it is called dark matter. Dark matter comprises 20% of our universe, and it's kind of like a cosmic glue or a kind of extra set of gravity that keeps all the stars in galaxies together. This is, again, invisible to us, and we cannot put in a test tube to measure this. So it is mysterious to us. However, we do know that in galaxies like this, or ours or others, there's really not enough gravity in galaxies to keep all the stars together. That is, stars should be randomly and chaotically just flying about, but the dark matter keeps it all together. We do know that in our solar system that planets closest to a large center of mass and gravity, that is our sun, orbit more quickly than planets to the outside. This is why Mercury takes 88 days to orbit our sun, while Saturn takes 30 years. And one would think that would be the case in a galaxy like this, or ours or others, where stars closest in to the center, where there's more mass and gravity, would go around more quickly than stars to the edge or to the outside, where there's less mass and less gravity. It only makes sense. But in study after study, and case after case, we find that stars uniformly travel at the same speed, about 250 kilometers per second, whether they are closest into the large center of mass and gravity, like the center of this, or further to the edge or to the periphery, where there is less mass and less gravity. And we attribute this then to dark matter. To be more specific, this is a computer simulation of dark matter. That is, wherever there's a large concentration of dark matter, galaxies form. Dark matter is the internal invisible skeleton of a galaxy. It is the internal scaffolding of a galaxy. Without dark matter, stars would just be randomly flying about, but dark matter keeps it all together. Thus, without dark matter, there would be no galaxies. Without galaxies, there would be no stars. Without stars, there would be no planets. Without planets, there would be no life. This is a pie graph of what the universe is made out of. Over 70% of it is dark energy. That is the force that makes space slowly expand. 20% of it is dark matter. That is the invisible kind of glue that keeps galaxies together. And the 5 or 6% remaining, that's what we can measure. Or if the whole universe was in this yardstick, the whole universe, then the first 25 inches of it would consist of dark energy. The next 8 inches, that is from 25 to 33, would consist of dark matter. And the rest of the 3 inches left, well, that's what we can measure. But we need special, sophisticated, and sensitive instruments to be able to pick up the light from more than 2 of these 3 inches. That leaves less than 1 inch of this that we can look through with our eyes. That is, in astronomy, we only see 1/36 of the universe with our eyes through telescopes. And this is why in astronomy there are so many questions as opposed to answers, and so many conundrums as opposed to solutions. We can hear me okay, Carl, back there? Thank you. Now these are galaxies that are hundreds of millions of light years away from us. And this is the oldest and farthest that Hubble can see back, which is 13.3 billion years back. And this all ties in to the Big Bang Theory. This theory postulates that the universe is 13.7 billion years old and started out with a primordial singularity. A singularity is a place or a point of infinite density. And this singularity contained all the matter of the universe. And this singularity did not explode, rather that it expanded and space expanded along with it. And within the first few seconds of it inflating or expanding, it had gone faster than the speed of light and had gone many times further than our distance of our solar system, dozens of times the distance, and it had gone faster than the speed of light. Because of this, it got super hot, up to 10 billion degrees. And because of this, then it was too hot for stars to form. And this was known as the Dark Ages. This stayed this way for 400 million years. It was just too hot. And this is why Hubble cannot see further back than 13.3 billion years back, because of the Dark Ages. And then at about the 400 million year mark, things got cooler and stars are able to form. Later on, galaxies formed. And about the 7 billion year mark, dark energy became more and more apparent. And now we live in the age of accelerated expansion, or cosmic inflation, where galaxies are slowly receding from each other. A bottom-to-top view of the Big Bang yields the same results. That is, the Primordial singularity expanded, space along with it. It became very hot. The dark ages occurred. Things started to cool down. Stars started to form. Galaxies started to form, as well as planets. And now we live in the era of accelerated expansion of the universe. Cosmologists believe that the universe will keep on expanding for billions of years more, and that dark energy will become more and more pervasive. So pervasive, in fact, that it will increase the distances between stars so much that galaxies will be broken apart, and stars will be aimlessly and loosely scattered about. And that the universe then will be a cold, distant, and remote place that will have no continuity or no congruity to it. It would be wonderful for our mathematical formulas if there was enough gravity in the universe to halt the expansion of the universe, and that for the galaxies to slow for the next 14 or 15 billion years, that the galaxies would slowly but surely all start coming back together to form the big crunch where this expansion can happen again. Sort of like an oscillating universe idea. But we don't think this will happen. Now, there are a lot of big elephants in the room with the Big Bang Theory. That is, where did this primordial singularity come from? How did it get here? What was there before? How did something contain all the matter of the universe? How come it expanded? How can something expand faster than the speed of light? How can something get so high? And there are thousands of questions, and all these questions are valid. And the answer to these questions is, well, we're working on it. We're also working on the grand unification theory, where we're trying to combine the three main forces in the universe, the strong, the weak, and the electromagnetic, into one grand equation to explain our universe. However, this has been hard because the strong force exists only on levels with temperatures that is of our sun. So the other two forces do not. So we're having difficulty with this. And if you throw gravity in with the mix, that is, if strong, the weak, the electromagnetic, and gravity, and put that into one equation, it is called the theory of everything. And we're having a little bit of a hard time with this too, because we're having a hard time marrying the macro, which is on the grand cosmological scales that we're talking about, with the micro, that is the subatomic levels or the quantum levels. This is because on the quantum levels, electrons have the probability, and quarks have the probability of being in one place than another. And since our laws of physics deal in absolutes, this is why we're having problems. Remember, our laws of physics do not play dice with the universe. And sometimes these theories that we're talking about, sometimes they say more about us than about the thing itself because of our obsessive need to find patterns in things. So we are dealing with that right now. But there is one main supporting pillar of the Big Bang Theory, and that is called cosmic background radiation. That means that there's a little bit of leftover heat, a heat signature, if you will, left over from the Big Bang itself. The universe should be negative 470 degrees below zero, but it isn't. It's a tad warmer than that. And this heat is uniformly distributed throughout the universe. This heat is very much akin to baking something in your oven for dinner, then turning the oven off, and then before you go to bed you touch the oven. It's a little bit warm, same thing. Now this is a plaque on Voyager, the one that's traveling at 38,000 miles per hour. It shows where Voyager comes from, and it has a pictorial of a man and woman. I'm interested in that because of all the elements that we are composed of. Each one of us here is composed of 8 gallons of water, 45 pounds of carbon, 2 pounds of phosphorus, a half pound of sodium chloride. Our bones and teeth are made of calcium. We have enough iron in our system. Well, we have enough iron to make a nail. We have trace elements. We have 15 different trace elements inside of us, like zinc, copper, lithium, magnesium. We even have 0.2 milligrams of gold inside of us. And our Earth is composed of trillions of tons of cobalt, nickel, iron, sulfur, silicon, tin, aluminum, manganese, boron. Where did all these atoms of all these elements come from? Well, they had to come from somewhere. They came from stars themselves. We are what stars are made out of. So in order to bolster that claim, we need to examine our sun. This is Mercury orbiting our sun, transiting our sun. Our sun is 860,000 miles in diameter. You could put 1,300,000 Earths inside the sun. Our sun constitutes 99.98% of all the mass in our solar system. It is 27 million degrees inside the core of our sun. How our sun works is it takes millions of tons of hydrogen per second, and through a process called nuclear fusion, converts that into helium. The resulting byproduct from that conversion is light and heat. That light and heat stays in the core of our sun and only wiggles out of it at the rate of 2 centimeters a day. And because our sun is so dense and so enormous, it takes thousands of years for that light to get to the photosphere of our sun, or then to us in 8 minutes and 20 seconds. Therefore, the sunlight you saw today was between 50,000 and 100,000 years old. Now, our sun is an average-sized star. It is middle-aged. It has been shining this way for 4.5 billion years, and will continue on shining this way for 4 billion years more. However, at that time, our sun will start running out of its fuel, hydrogen. When that happens, the core will contract and get smaller, and that means the sun will heat up to tens of millions of degrees more in temperature. This will then evaporate the Earth's oceans and make the inner planets of Mercury, Venus, and Earth all molten. And because the inner pressure of our sun will not match the outer pressure of outer space, our sun will start to blow it out or get bigger and bigger. And over thousands of years, our sun will get bigger and bigger and go out to almost to the orbit of Mars, where it will become a red giant. And these are some red giants in our Orion arm. Antares is 1,000 times bigger than our sun. Betelgeuse is 800 times bigger than our sun. And our sun will become a red giant and stay that way for thousands of years. And then one of two things can happen to a red giant. A star that's more massive than our sun, one that's in the diameter of millions of miles, more robust, well, that what they call supernova. That is, the outer shell will go out into space, be disseminated in space. Our sun will not be so dramatic. Oh, there'll be no loud bang from this supernova here because there's no air and space to carry the noise. Our sun will not do anything so dramatic. Our sun's outer shell will just disintegrate into space, being an average-sized star, and it will look like this. In either case of a supernova or a disintegration, what's left over is what they call a stellar remnant or a stellar nebula, which is what you're looking at. There will also be a core left over, of which we'll talk about later on. However, right now we'll focus on the outer shell of the sun, or the stellar nebula, because it contains a lot of elements that can make new worlds. That is, during the course of a lifetime of a star's existence, it has accumulated trillions of tons of space dust, comets, asteroids, rocky debris, meteorites, and other planets, and is very rich in building blocks to make other worlds. However, stars do not contain amino acids or DNA to start life. Now, this outer shell of the sun, or a stellar nebula, then becomes disseminated into space and drifts out into space for tens of millions, hundreds of millions, or even billions of years. And sometimes these outer shells of suns bump into areas where new stars are being formed. This is in the Large Magellanic Cloud, 200,000 light years from us, like we talked about in our local neighborhood. That is, outer shells of suns, stellar nebulas, run into these areas and help seed and nucleate these new areas with new materials that can make new planets and stars. The same is true then of these stellar nurseries in the Pillars of Hercules, 1,600 light years in the Orion arm. That is, stellar nebulas run into these areas and help seed and nucleate these new areas. And the exact same thing happened 4.5 billion years ago when our solar system was being formed. That is, suns in the Orion arm or in the Perseus arm or Sagittarius arm. Well, the outer shells of those exploded or disintegrated, and those then came in contact with our newly formed area to help seed and nucleate our area with essential elements that make our world up and us up. Therefore, We are what stars are made out of. And conversely speaking, when we pass on, those atoms of the elements that we have been talking about, say atoms of calcium, lithium, carbon, they will still stay on here on Earth. They will never die because they've never been alive. Those atoms in our body that constitute us have been around for at least 10 billion years and will continue on being around since our galaxy was formed, and will continue on being around for billions of years more. Therefore, when our sun becomes a red giant and encompasses Earth and later on disintegrates its outer shell into space, your atoms in your body will be disseminated in space along with that disintegration. And one day, billions of years from now, those atoms that constitute you might run into areas where new stars are being made, that is stellar nurseries, and might seed and nucleate those new areas with new materials that can make stars or planets. So cosmically speaking, what goes around comes around. And please note that matter cannot be created or destroyed. Rather, it can be recycled, rejuvenated, or regifted into other forms of matter or other forms of energy. And thus, the same is true with the information inside an atom. The information that is on how the electrons spin, how the quarks are arranged, what kind of quarks there are. That information needs to be saved, and it can't be created or destroyed, and we will talk about that then when we talk about black holes. Now, 60% of all stars in all galaxies are red dwarfs. We talked about a red dwarf with Alpha Proxima. Red dwarfs are much smaller versions than our sun, less than half the size, and that means that they use up their hydrogen very efficiently. These red dwarfs will never become supergiants, red giants, nor will they explode, become supernovas, nor will they disintegrate in space. Rather, they have been shining this way for billions of years and will keep on shining this way for billions of years more to come. They are very steady state. Now, our sun, we talked about the outer shell disintegrating into space, but what's left is a core. And the core of an average-sized sun, like our sun, then becomes a white dwarf. And the white dwarf is about the size of Earth and is a very hot, heavy iron ball. How did it get to be iron? Well, you remember that hydrogen that was converted into helium through nuclear fusion? Well, that helium in the core of our sun undergoes changes, and it's called nucleosynthesis. And those changes means that over billions of years, the core then changes into carbon, which changes into other elements that become iron, which cannot be broken down. So this white dwarf will be about 2 or 3 million degrees in temperature and give off light and heat, but in a very feeble and impotent fashion. So now we've talked about stars that are smaller than our sun. They become red dwarfs. Average-sized stars like our sun has a core left over, and those are called white dwarfs. Well, what about larger stars than our sun? Larger stars than our sun constitute between 10 and 15% of all stars in all galaxies. You say, 10% is no big deal, but in our galaxy's case alone, it's 10% of 300 billion is 30 billion. That's a big number. So stars that are between 1.5 to 2.5 times larger than our sun, obviously the shell will be blown up into space, and what's left will be a very heavy core. And the core of this becomes a neutron star, of which I need to show you what it looks like. And a neutron star I'm getting there. And a neutron star really, really warps the fabric of space. They call it a neutron star because the electrons squash the protons, and since there's no charge between the electrons, more matter can be squeezed in between spaces. And a neutron star will be about the size of Manhattan and will give off about 10 or 12 miles in diameter, and will give off light and heat and spin, but it'll be a super concentrated heavy ball. And a teaspoonful of this neutron star will weigh 1 billion tons, as much as Mount Everest. And that if you get anywhere near its gravitational well, excuse me again, you get anywhere near it, well, if you get anywhere near its gravitational well, you'll be slammed into it. However, if you can manage, for the sake of argument, to land on it, you never get off of it because the escape velocity is 90,000 miles per second, or half the speed of light, where our escape velocity on Earth is 7 miles a second. Now, a neutron star will have an atmosphere that's 4 inches thick and be composed of liquid diamonds. There are tens of millions of neutron stars in our galaxy alone. Now, another kind of neutron star is called a pulsar. And a pulsar is really a neutron star that spins very, very fast. And the electrons get super excited and gravitate toward the poles, where then they give off light on the poles, and it ends up looking like this. It ends up spinning and giving off light like a lighthouse beacon coming at us. And most times, these pulse at us at thousands of times per minute, sometimes tens of thousands of times per minute, sometimes even hundreds of thousands of times per minute. So that's what they call a pulsar star, which is really a neutron star that has light shining out of its poles. Thank you. Thank you. And then there's another kind of neutron star called a magnetar. A magnetar is a neutron star with an intense and immense magnetic field. And sometimes these magnetars give off FRBs to us, or fast radio bursts, every 90 minutes. And if you get within 500 miles of the magnetar, it'll rip your atoms right out of your body. So these are some of the gravitational signatures of what we've been talking about today. Our sun waits down space. A white dwarf, which is the core of an average-sized sun like ours, waits down space further. And then a neutron star, which is a star that's between 1.5 to 2.5 times bigger than our sun. That'll wait down space even further. And the ultimate example of this is a black hole, of which we'll talk about next, and everybody's favorite subject. A black hole is really a place where gravity overwhelms the speed of light, hence it's black. And what's going on here is that when the sun is the sun is 2.5 times bigger than our sun, or it could be 5 times bigger or 10 times bigger, well, that shell of the sun explodes off into space, and what's left is a core. And that core then implodes and becomes a singularity, or a place or a point of infinite density. And like we talked about with the Big Bang Theory. And the morphology of a black hole looks like this. That is, matter is accreted from a companion star and swirls around at the top, and it's called an accretion disk. Beneath that is an event horizon, that is, where light cannot escape, hence it's black, and beneath that is a singularity, or the place or point of infinite density. Now, we'll talk about a stellar black hole here with a diameter of about 20 miles. Now, just how do scientists figure out where a black hole is if they can't see it? Well, 60% of all stars in all galaxies are binary. That means they have companion stars. We talked about a companion star with Alpha Proxima. Our solar system almost had a binary system, but Jupiter is really a failed star. It needed to be 1,000 times bigger. So we have a failed star. However, scientists then look in the sky and they see a companion star orbiting where there's nothing there. And this companion star will have a wobble to it, or what they call a perturbation, which means it's being pulled on by something invisible and intense inside of its orbit. So that's how they infer that it's there. Now, a very dramatic representation of it looks like this. Matter is siphoned off from a companion star and goes around on the accretion disk. This companion star, by the way, is tens of millions or hundreds of millions of miles away. Matter then is accreted on an accretion disk and swirls around and around. But it swirls very, very fast and becomes superheated. So hot, in fact, that some of the material then is ejected and becomes what they call plasma, or superheated matter, and can be ejected from the tops and bottoms of the accretion disk. Also, the superheated matter emits X-rays, which we cannot see, but can be detected by observational satellites above our head. And that's how they know a black hole is there. They infer it with the companion star, and it's also a fantastic source of X-rays. So again, matter is accreted on an accretion disk from or siphoned off from a companion star. And if there's no companion star, then any space dust or debris will do. So what would happen if you fell into a black hole? Well, in order to do this thought experiment in theoretical physics, you would need an observer, that is someone who watches and observes things, as well as someone who doesn't. We're going to have two astronauts in space, both wearing spacesuits, both having radios. Astronaut Jane will be our observer. She will be well away from the black hole, out of harm's way, but will be able to watch and observe her astronaut friend, Bob, go into the black hole. Jane's in charge. Jane radios to Bob, let's start this show. Bob dutifully goes around the black hole and starts spinning around. To Jane's amazement, going slower and slower, he becomes redder and redder, he becomes redshifted, and becomes fainter and fainter from view. Then Bob goes into super slow motion, becomes bright red, and then just disappears from view. Jane immediately gets on her radio and tries to contact Bob. But Jane's radio waves never reach Bob because they've been overwhelmed and overtaken by gravity. Jane says, well, can't reach him on the radio, can't see him anymore. This show's over, I'm out of here, what's for lunch? Bob, on the other hand, has a much different experience. When Bob goes into the black hole, he looks up and there's no stars above his head. That is, it's all black. And this is because the light from those stars has been overtaken and overwhelmed by gravity just before it reaches his eyes. Then Bob looks at his watch and realizes that time is slowed down by half. That is, gravity drags down on time. And we know this because there are 31 GPS satellites above our head. Each one of those satellites has an individual clock on it, and each clock is 1/3 of a millionth of a second faster than the ones on Earth. That's because the clocks on Earth have been slowed down by Earth's gravity and mass by just a little bit. And if those clocks aren't reset, by the way, every day, you're going to be off 6 miles on your trip. So going back to Bob, Bob's all excited about what he's learned about light and about time and wants to radio Jane about his news. So Bob gets on the radio. However, Bob's radio waves never reach Jane because they've been overwhelmed and overtaken by gravity. Well, Bob's in a conundrum here. And then he has an epiphany. And he takes out his handy-dandy astronaut flashlight and says, I know. I'll signal Jane with my flashlight using Morse code to tell her about my new finds with light and time and how I'm doing out here. Well, as you can guess, the light from Bob's flashlight never reaches Jane because it's been overtaken by gravity itself. Now Bob's in a true existential dilemma. He's in the universe's most fantastic place, a place where we all want to know about it, but literally can't get the word out about it. And then one of two scenarios can happen to Bob. In the first scenario, Bob falls into the black hole head first. Because Bob's head is closest to the center, his neck starts feeling stretched, his body starts feeling elongated, and through a process called spaghettification, Bob is stretched out thinner than the width of a human hair. Obviously, Bob dies. In the next scenario, Bob goes into the black hole, and as he gets nearer to the event horizon, the information about Bob and his spacesuit is saved. That is, the information on how the atoms are arranged, how the electrons spin in each atom, how the quarks are arranged, what kind of quarks they are. That information is saved because it can't be created or destroyed. And the information is saved as a hologram. And so there's a hologram of Bob in a spacesuit floating just above the event horizon. Well, all a hologram is a two-dimensional representation of a 3D object. And now that the information is saved, the universe is in harmony, and Bob now can fall into the event horizon and be squashed or spaghettified. We needn't worry about this happening to any of our astronauts or our space probes because the nearest black hole is V616 Mon. It is in Monoceros. It is 3,000 light years away. The next nearest one is Cygnus X1 in Cygnus, which is 6,000 light years away. Now, it is said that if you could successfully fall through a black hole, you end up going through a wormhole. And a wormhole is really a nexus or a portal to a different part of our universe, a different dimension, or even a different time frame. And how a wormhole works is in standard Newtonian physics. You go from point A to point B in a straight line. However, in Einsteinian physics, space is curved and warped by massive gravitational objects, and you go from point A to point B like this. And this is pure nonsense, however, because as soon as you fall into a black hole, you're dead. And all that wormholes are great plot devices for science fiction books and movies, which is where they belong. Now, it is said, not as said, but when scientists look past black holes, they see this, which is a real picture. That is, they see past the black hole, galaxies and stars optically pop out at us. That means they look larger and closer to us. And all this is an optical illusion due to the distortion of space. Now, people often ask me, Mr. Shepard, what's it like being in a black hole? I see it's a place where our laws of physics really need to be amended to handle these unique circumstances. And then people ask me, well, what's it really like being in a black hole? Get down to it, would you? And I say it's a really weird and bizarre place. I say it's really a place that's not too far from us, a place where scientists are baffled by the fact that at this place, or this look-alike black hole place close to us, that there's no life on it past 8:30 at night. Perhaps you know of it. This is what happens with the life cycle of a star then. An average star like ours, like our sun, becomes a red giant that becomes a planetary nebula that ultimately becomes a white dwarf. A much larger star than ours, one that's in the diameter of millions of miles, then becomes a super red giant. It becomes a supernova and becomes a neutron star, pulsar star, magnetar, or a black hole. Now, the last subject we'll talk about today is quasars. Quasars are called quasi-stellar objects. They are really galaxies that are receding from us at 95% the speed of light, and they are billions of light years away from us. And in this pictorial here, it shows jets of matter coming out. That's because in the middle of all quasars that really give off tremendous amounts of energy, and in the middle of all galaxies are galactic black holes. And sometimes these can give off streams off jets of matter, like in this pictorial here, which is really an illustration, but really what it looks like is this in reality. This is in Hercules 1A, 1.5 million light years from us. That is, there's a black hole here, and it's shooting out jets of matter like we talked about in the previous example. And what's going on then is in the middle of all galaxies, including ours, are galactic black holes that are really graveyards of old dead suns. We have one in the middle of our galaxy. It is 26,000 light years away. It's in Sagittarius. The diameter of the black hole in our galaxy is 15 million miles. And what's going on is that in all galaxies this is happening. There are just millions of dead suns in the center of them, and they are accumulating a lot of debris from the galaxy. And they are spinning it around on a huge accretion disk that's millions of miles in diameter. And it spins around so fast that it goes around so quickly it superheats and turns into light. And this is why in the center of all galaxies, that is why they're so bright and luminous, because of these galactic black holes. These black holes consume about 15 Earth masses in about 10 years. So there's one in every galaxy, and we are just starting to learn more and more about this. In order to do that, we'll be sending the James Webb Telescope up at this time next year from Guyana, South America. And the Webb Telescope then will ultimately replace Hubble, because Hubble's mirror is only 7 feet in diameter, while the Webb Telescope will have a 31-foot diameter mirror made up of hexagonal cells. This telescope then will go out into space 1 million miles from Earth, that is 4 times further than the Earth is to the Moon, and be stationary out there. And to protect it from the sun's damaging heat, it will have a heat shield on it the size of a tennis court. It'll weigh 7 tons, it'll be cryogenically cooled, and we'll be able to see to the very, very edges of the universe, and we'll see in different kinds of lights, like infrared and ultraviolet and other kind of light rays we have not discussed here today. This should help us tremendously with our examination of the universe, and should see much further than Hubble, and should be much clearer, and may see to the very edges of the universe, where we might see this, or this, or this, and hopefully we will see this. And that is the end of my presentation. Thank you very much.